Hi everyone, this is Miss Evangelista again, and this is video 4.2, Discontinuous Points. Today's objective is that you will be able to determine points of discontinuity of rational functions. You will need your calculator for this video, so please make sure you have it out. Okay, let's start with an example, somewhat of a review of what you should already know, but let's do it together. Let's find the simplified form of the function x squared minus 16 over x minus 4, and we'll find the asymptotes x and y intercepts. Okay, so the first thing we want to find is the simplified form, which you can see the answer. Okay, the simplified form. What I mean by that is look at the numerator and denominator and see if there's a GCF that can be factored out, or if something can be factored. Well, hopefully you're looking at that numerator, x squared minus 16, and thinking difference of squares. X squared minus 16 can be factored as x minus 4 times x plus 4, and the x minus 4 in the denominator just stays there. Well, this still can be simplified because we know that x minus 4 on the top and the x minus 4 on the bottom can be factored out, or can cancel each other out, and that just leaves us with the x plus 4 on the top. So this is the simplified form of our rational function. Okay, so from here on out, whenever you are given a rational function, your first step is always to try to simplify it first. Okay, now vertical asymptotes. How do we find our vertical asymptotes? Well, we set the denominator equal to 0. However, notice that we have two equations that are essentially theoretically equal. Which one do we want to look at when we're figuring out the asymptotes and x-intercepts now? Okay, from here on out, we're going to use the simplified form. So I know that to find a vertical asymptote, I set the denominator equal to 0. Is there a denominator of a linear function of x plus 4? Well, yeah, theoretically, we know that it is over 1, right? But if we set that equal to 0, 1 obviously does not equal 0, so we see that we do not have a vertical asymptote. Horizontal asymptotes. Remember, for horizontal asymptotes, we compare the degree of the numerator and the denominator. Well, let's see. In this case, the degree of my numerator is 1, because x is to the first power. The degree of my denominator, again, it's over 1, which is a constant, and I know constants have an exponent or degree of 0. So in this case, we have a top-heavy equation, which means that there is no horizontal asymptote. Okay, x-intercepts. To find the x-intercepts, I set y equal to 0 and then solve for x. If I set y equal to 0 and solve for x, I get x equals negative 4. Okay, so my x-intercept is negative 4. My y-intercept, I set x equal to 0 and solve for y. And I know f of x can be rewritten as y. So y equals 0 plus 4. I have a y-intercept at 4. This should be a review. Now what I want you to do is graph f of x using your calculator. So in y1, you're going to type in the original function, so type this in. Now, when you're typing that into your calculator, make sure that you put parentheses around the numerator and denominator. Okay, this can be very important when we look at graphing. Okay, so that's how you should type it in. Go ahead and type that in and see what it looks like. Alright? Since you graphed on your calculator, this is what our rational function looks like. Looking at this, you might notice that this is the graph of a linear function. But clearly, our function, our original function, is a rational function because we have a polynomial on the top and a polynomial in the denominator, but this doesn't look like a rational function. It doesn't have the branches like it normally does and the horizontal and vertical asymptotes. Okay? What I want you to do now is type in the simplified form of f of x, which remember was a linear function, x plus 4, and I want you to type that into y2 in your calculator. Okay, go ahead and pause the video, do that now, and then graph it. What you should notice is that the graph of both functions, the original and the simplified form, actually they do look the same, right? So that's what you should notice. Both graphs look the same. However, I want you to ask yourself, is it possible for the graphs to be the exact same graph? Pause the video and think about it. Okay, well, let's answer that question by comparing our original function to our simplified function. Okay, if we're looking at the original function, what is the domain of this function? Okay, remember, domain is all of the possible x values. Okay, what you should be thinking is, well, if I put a 4 in the denominator, it would make this function have a 0 in the denominator, and I know that's not possible. So our domain of the original function is all reals except x equals 4. X cannot equal 4, because otherwise the function is undefined. However, if we look at the simplified form of remember, it's a linear function. I can put any x value into our function and get some y value. So our domain of the simplified form is all reals. But you're thinking, the graphs looked the same, okay? Now, what I want you to do is clear the simplified form from your calculator. Remember, we typed that in as y2. And I want you to just have the original function typed in for your y1. And pull up the table using second graph. And I want you to look at fill in this table for the y values between x equals 0 and x equals 5. Go ahead and pause the video and fill out this table. Okay, we're back. Here is the filled out table. This is what you should have noticed. Okay, we have y values for all of the x values except for x equals 4, which makes sense because if we look back at our original function, we said the domain is all reals except for x equals 4. Okay, what does this mean? Okay, this was our graph, remember, when we graphed it. This graph looks connected for this entire graph, but what we find is that it's actually not. At x equals 4, here is x equals 4. Okay, where is the y at x equals 4? Draw a straight line. At x equals 4, we have a hole. There's a hole in our graph, and this is what we mean by point discontinuity. We have point discontinuity at x equals 4. Okay? All right. So remember, this was our original function. Think back about how we might have been able to find, or how we could have been able to determine that there was a hole by looking at this equation right here. Okay? Well, if you recall, I'm going to move back. When we were first looking at our original function and we were trying to find the simplified form, notice what happens right here. Oops, right here. Okay? There was a factor of x minus 4 in the numerator and the denominator, and we were able to cancel those out. Okay? And it just so happened that we also had a hole. There was a hole at x equals 4. Okay? So if we were to take that factor that was in the numerator and denominator, set it equal to 0, and solve, what we get is the location of a hole in our graph. Okay? So going back, how can we tell when there is a hole in the graph? By looking just at the equation. There's a hole anytime that when we factor our equation, there's a common factor that can be canceled out in the top and the bottom. How about if we were just looking at the graph? How could we tell if there's a hole in the graph? Well, actually, it's harder by just looking at the graph, because when you graph the function on your calculator, it will actually appear like the graph is connected, but it's not. However, using the equation and your intuition, you can look at the table of values and see where there is an error, okay? But just because there's an error does not necessarily mean that there's a hole. It could be a vertical asymptote or horizontal asymptote, and that's where we normally will look at the equation to tell if there is a hole in the graph, okay? All right, your turn to try. Go ahead and copy this example down, and what you're going to find is the simplified form, asymptotes, intercepts, and any points of discontinuity. And remember, you're going to factor or simplify first. That's always your first step. Go ahead and pause the video and work this problem. Okay, we're back. Here is the original function. First thing I want to do is simplify this. Well, the numerator can be simplified, can be factored as x minus 2 times x plus 1. The x minus 2 factors cancel out and leaves me with a simplified form of f of x equals x plus 1. Vertical asymptote set the denominator equal to 0, and remember we're looking at the simplified form. There's no denominator. That means there's no vertical asymptote. Horizontal asymptote. Remember, we're comparing the degree of the numerator and denominator. This is a top-heavy case, which means there's no horizontal asymptote. X-intercepts. Set y equal to 0, solve for x. You get an x-intercept at -1. Y-intercept. Set x equal to 0 and solve. We have a y-intercept at 1. And our point discontinuity. This is what you were looking at. How did you simplify this form? What factors were common in the numerator and denominator? Well, it was the factor x minus 2. Okay, that was common. We're going to set that equal to 0 and solve. And so we have point discontinuity at x equals 2. And if we look at our graph, this is what we find. We can verify our answer by looking at the graph. Our x and y intercepts match what we have. And point discontinuity, if you look at the table, you'll see that at x equals 2, there is no y value that corresponds. Okay, did we meet our objective? Students will be able to determine points of discontinuity of rational functions. Go back through this video if you need extra help, or see me before school or at lunch. See you guys tomorrow.